Greetings, calculus students. We're going to be continuing our notes on related rates right now. I'm going to want you to pause me real quick, look back at your old notes, and write a one-sentence summary of related rates at the top. So look back at the previous notes and write a summary of related rates at the top. Okay. So yeah, you can think about related rates as like the mathematics of change is what it says on the previous page. You can also think of derivatives. You're looking for derivatives because derivatives represent change. You're looking for how much something has grown, for how much something has shrank, how much something has changed. So you're looking to identify the instantaneous change. The reason why I say instantaneous is because there are other methods of detecting change that are not instantaneous that will give us approximations. So an approximation is something that you can find using algebra. So let's look at this first problem. Oh, sorry, before we do that, also at the top, somewhere around where your sentence is, I just want to remind you of some important areas that you're going to have to memorize. It will make your life easier to just memorize these instead of looking them up every time. But we're going to be dealing a lot with area and surface area and some equations that you probably haven't thought of in a while are areas of spheres and of cones. So the area of a sphere is 4/3 pi r cubed. The area of a cone is 1/3 pi r squared times the height. The surface area of a sphere is 4 pi r squared. And the surface area of a cone is pi r squared plus pi r L, where L is the slant height. If you don't know what I mean by slant height, go ahead and just Google cone slant height. You'll see a nice picture of that. This thing. I guess I'll just show you because that's the way I am. That's the slant height. Okay, now let's do this problem. Lo siento, I'm sorry for being confusing. So if the radius changes 0.1 centimeters, a very small amount, how much does the volume change? Okay, so we want to figure out the change in volume if a radius started at 10 centimeters and then changed by 0.1. So the volume of the sphere I don't know why I wrote area up here. This should be, I'm so sorry, this should say volume. So the volume of the sphere is what we have up top, is 4/3 pi r cubed. And in this case, r equals 10. That's what we're starting out with. So the volume is 4/3 pi 10 cubed. If we plug this in our calculators, we would get 4,188.79 centimeters cubed. So that's the volume when the radius equals 10. And it wants us to figure out if the radius changes by 0.1, how much does the volume change? So instead of plugging in 10, we're going to plug in r equals 10.1. So this volume will be 4/3 pi 10.1 cubed, which is equal to 4,315.715 centimeters cubed. So the change in volume would be the difference between the volume when we plugged in 10 and between 10 and 10.1. So subtracting those two values, or finding the difference between them. And then we get that it changes by 126.925 centimeters cubed. So this is how much the volume has changed by. Okay. So just changing 0.1 of a centimeter, the volume changed quite a bit. This is an approximation though. This problem down here, we're going to use calculus to find the instantaneous rate at which it's changing. Okay? Think back to when we first learned about the derivative. The easy definition that you use for the derivative was instantaneous rate of change. This is your very early definition of a derivative that we need to continue thinking about. This is very true still. So we're going to use the derivative to find that instantaneous rate of change. And we want to find how much the volume is changing when the radius is changing by 0.1. So let's just write down everything we know. We know that the radius equals 10, and the change in the radius, dr dt, is 0.1. It's the instantaneous change of the radius. We still know our volume equation is 4/3 pi r cubed, but we can find the instantaneous change in volume by calculating dv dt. The derivative here, dv dt, take the derivative on this side, would be 4/3 pi times 3r squared. Obviously these 3's will cancel out and we get 4 pi r squared. Oh, I forgot something very important, and that's because here we took the derivative, let me use another color. We took the derivative in terms of r, so I needed to add here a dr dt. And again, here I have dr dt. So when we have multiple variables, anytime you take the derivative in terms of that variable, you have to add that dr dt. Similar to when we were doing implicit differentiation. You use different implicit differentiation when you have both an x and a y variable. So we always had to remember to write dx dx or dy dx. But in this case, we're going to write dr dt. So it's always going to be over dt because rates of change happen over time. So we want that dt, and our variable is r, so it's dr. Now we can plug in what we have for the radius and what we have for dr dt into this equation. So this will equal 4 pi 10 squared times 0.1. That ends up being 125.664 centimeters cubed.
Call the main office, Mrs. Chen. Can you please call the main office?
Yes, you can still hear the announcements because I'm staying late at school on a Friday. So this is the instantaneous rate of change of the volume when you change the radius by 0.1. This is an exact answer. So our approximation was actually pretty close, but this is it exactly. Not a bad approximation though. Okay, so this is a related rate problem. On the next page, you have this up here. I want you to actually skip down to this one down here. These are the steps for related rate problems. Please pause me and read through these steps. Hit pause and read through the steps. Okay, so these steps are fairly similar to that for optimization. It's always a good idea to start drawing with a drawing or a sketch so that you can visualize what is happening. Write down any information you know And this is going to include, when you write down the information you know, you should also assign those variables. So assign variables, for example, you might, like in the previous problem, you might say r equals 10, dr dt equals 0.1. These are things that we knew in the beginning. Then you should write down what you want to find. So we would say find dv dt. That's what we were looking for. We wrote an equation that related the variables. We said that the volume equaled 4/3 pi r cubed. This related everything that we knew. We took the derivative, we found v prime, and then we substituted in. Well, we didn't do, I was bad. I didn't rewrite it as a sentence. That's what they had here. The sphere is growing at a rate of, there. So this would be my sentence that we use to finish it off. Okay, so these are steps to keep in mind for rates of change. And now, let's look up at this cylinder problem. I'm going to add a little bit of information that's kind of missing from the cylinder problem. I'm going to add this radius. I'll say the radius is 4. Here's my picture of my cylinder. So this problem says water is draining from a cylindrical tank at 3 liters per second. How fast is the surface dropping? Let's add some water to give us some visualization. So figuring out how fast the surface is dropping, basically this water is going to be going down, down, down. What the surface of the water represents, this is like the height of the water. Okay? Because we're taking the volume not of this whole cylinder, we're taking the volume of the water. Okay? So finding the volume of the water means that this mark here would be my height. Okay. So we already have a picture. We can define some variables. So my radius equals 4. Water is draining from a cylindrical tank at 3 liters per second. This is implying that the volume is changing at 3 liters per second. So dv dt is going to equal -3. Okay, that's all I know. I guess I could also say about my variable r, that dr dt, the change in the radius, that's never changing. So that just equals 0. Since I had an r, I can find dr dt, that's just 0. Alright, so the next step is write down what you are looking for. So I want to find how fast the surface is dropping. So how fast, that represents a rate. So I'm trying to find dh dt. I'm finding how fast the height is changing. Okay. So now we are going to write an equation to relate the variables. In this case, we can relate the variables using the volume of a cylinder, and that will include the radius and my height. The volume of a cylinder is the area of a circle, so this pi r squared, times the height. So I've related both of my variables here. Now I can take the derivative. Since I have 2 variables, I'm going to have to use chain rule. So dv dt equals, let's differentiate first in terms of r. So I'll take the derivative in terms of r. We have 2r times h dr dt plus pi r squared, taking the derivative in terms of h, leave this as 1 dh dt. let's plug in what I have. dv dt is -3. The radius is the radius is 4. I do not know the height, because that's changing. dr dt is 0, plus pi times the radius squared, dh dt. I don't know dh dt, that's what I'm looking for. So one good thing is that this whole term is going to cancel out because it's 0. This is a pattern that you're going to start picking up on because you're going to have a lot of constant variables, like this variable actually wasn't changing at all. Technically, we didn't really have to take the derivative in terms of it because it's going to go away anyway. Since it's a constant variable, it's going to go away anyway. But if in the beginning you want to just take the derivative in terms of everything, that's fine. But if you recognize that if we take the derivative in terms of a constant variable, it's just going to go to 0, you can kind of skip this step. Okay, let's simplify. So -3 equals 16 pi dh dt. Now I only have my one unknown, and this is what I'm trying to find. So dh dt equals -3 over 16 pi. So this answer makes sense. We got a negative answer, which is representing the surface dropping. Since the surface is dropping, it's going in a negative direction. The height isn't growing, it's dropping. So this answer makes sense. And we can rewrite it as a sentence. So the surface is dropping at a rate of -3 over 16 pi liters per second. Okay. And that's it. We'll do one more example. So flip the page. It's the last page of the packet because we skipped a whole bunch of pages. So this last page is just one problem split up into all the different parts. So this is going to kind of guide us through all those steps that are on the previous page. So truck problem. A truck Truck A travels east at 40 miles per hour. Truck B travels north at 30 miles per hour. How fast is the distance between the trucks changing 6 minutes later? Okie dokie. So let's just start with step 1. Draw a picture. Honestly, they already helped us a lot. This is going to be a picture that you'll have to draw a lot when you have problems that are asking for distance between them. Remember, I talked about this word distance and how distance is really related to the Pythagorean theorem. So if truck A is traveling east, he's going this way, and truck B is traveling north, you can kind of form the legs of your triangle. So here is my picture representing that. Gorgeous. So now let's write down what we know. These two sentences tell us the rates of change of the cars. Never mind. So I'm just going to use the variables A and B. So the change in the distance that truck A is traveling is going to be dA dt equals 40. Thus, we can figure out the change in B. dB dt equals 30. Oh, but this problem's being very tricky. They're very sly. So one thing I just noticed is that they give these rates in miles per hour, but they want you to figure out an answer in minutes. So I'm just gonna right away convert these from miles per hour to miles per minute. So if this is miles per hour and this is miles per hour, the way that you can calculate miles per minute would be to divide by 60. So 40 divided by 60 is going to be 2/3 miles per minute. You can pause if you need to go figure that out. And then 30 miles per hour, again I would divide by 60 because there's 60 minutes in an hour, would be 1/2 miles per minute. That was very tricky of this problem. I do not appreciate it, switching the units like that. Alright, so those are the things we know. We can also solve actually for A, figure out what A and B are, because it tells us that it's 6 minutes later. So if they started here, how far had A traveled in 6 minutes? Well, if you know he's going 2/3 miles per minute, that means in 6 minutes, let's multiply this by 6, he's going 4. Or I'll show my work. He's going 2/3 times 6 minutes equals 4 miles. And then car B, if he's going 1/2 mile per minute, then in 6 minutes he's going 3. If I know this side is 3 and this side is 4, using the Pythagorean theorem, I can quickly find this side. I'll call it C. This C equals 5. Ooh, my triangle's kind of messy. I'll zoom in here so you can get all those. Okay. And then what we want to find, so what do we want to find? We want to find how fast is the distance between the trucks changing. So this value C is the distance between the trucks, and we want to figure out how it's changing. So what we're trying to find is the value of dc dt after 6 minutes. Okay, so we're trying to find dc dt. Next step. Step 4, it doesn't really say here, but I'll write underneath. Step 4 is to write an equation that relates the variables. So we need an equation that will relate all our variables. We have this really nice right triangle. So the first equation that comes to my mind is x squared, or no, not x, a squared plus b squared equals c squared. Pythagorean theorem. It relates all my variables, so I can move to step 5, which is to differentiate. Okay. The derivative of this will be 2a dA dt plus 2b dB dt equals 2c dc dt. And step 6 is to substitute what you know in. So go ahead and look up at your known values. Don't look at me. You know all the values. Substitute everything that you know in here. Go ahead, hit pause on me. When you play again, I'll have the value here. So hit pause as you substitute those values. I'm running out of space. Here, equals 2 times 5. Okay. I kind of ran out of space, so that's ugly, but oh well. So everything on the left side we knew. The only thing that I don't know is dc dt, which is great because that's what I'm looking for. So to simplify this left side, I get 16 over 3 plus 6 over 2 equals 10 dc dt. If I combine these, we would have 25 over 3. Is that really correct? I need to check that real quick. Oh! 3, 9. Oh yeah, that's totally right. Okay, 25 over 3 equals 10 dc dt. And then the last step is to divide by 10. So that's 25 over 30 equals dc dt. And if we simplify, we get 5, 6 equals dc dt. So the last step is to write the sentence. With the answer. So that would be, the distance between the trucks 6 minutes later is changing at a rate of 6 miles per minute. Which totally makes sense. If you look back at your picture, so we have 6 miles. It went 5 miles, that's the distance, after 6 minutes. So conceptually, this makes a lot of sense. After 6 minutes, it had gone 5 miles. Cool. I'm going to post some homework on related rates. I encourage you to get started over it on the weekend so that when we come and work on it in class, you aren't starting from scratch. I've noticed that when we start from scratch, it takes us so much longer to complete like 2 problems. It takes us like 30 minutes to finish 2 problems. So go ahead and try some problems on your own, and then when you come in, you'll be more prepared to engage with your teammates. Either way, have a good weekend. Don't forget to like and subscribe. Bye!